Hello everybody, and welcome to module dealing with the analysis of variance. So this is one of the key things that we want to understand in our introductory course to educational statistics. And we've been working up to analysis of variance, believe it or not, and basically all that we've been doing. This is a powerful statistic test that is used quite often in various forms. We're going to look at the most basic form of ANOVA. Analysis of variance is called ANOVA, and that will be a one-way ANOVA, and we'll briefly touch on the other ideas in that. But this is kind of a crowning achievement that you've made it this far. So congratulations. So with that, let us begin by looking at the goals of this module. So our module goals are to compare and contrast the purposes of analysis of variance and an independent t-test, which we did in the last module. Discuss the rationale for analysis of variance. Compute the necessary values to complete an analysis of variance summary table for given data sets. Determine when an a posteriori test or post hoc test is appropriately applied. Interpret a statistically significant F value from an analysis of variance or a post hoc test. Use the F table to determine the critical value for F. And then describe two components of variability in an analysis of variance, the two components. So that is where we're going to start today with these goals in mind. So let's actually begin with a review of what we've been looking at. So far, we've learned that we can compare two groups by conducting our t-test, which compares the variances and the means of the groups. So in the t-test, we learned that we had three different t-tests to choose from for our analysis, whether it was a dependent test or an independent test that had the same variance or an independent test that had the separate variance. In the background, what we were doing is we were comparing the variances and the means of those tests or of those groups to see how different they were. Okay? So we learned that, like I said, the dependent t-tests are conducted when we have one group that has two measurements. The most common form of this may be a pre- or post-test approach, and we saw some examples of that. We've learned that independent t-tests are conducted when we have two groups, such as a treatment group and a control group, and then we talked about the fact that we have two types of independent tests, whether our variance is equal or whether it's not equal. And then we conducted an F-test before getting to our actual independent t-test to see whether or not the variance was equal. And that F-test was simply we took the larger variance and divided by the smaller variance and then compared that to the F distribution chart that was provided. So what if we wanted to compare more than two groups? Okay, so in the past we simply compared two groups, Class A and Class B, a pre or post test or something like that. But what if we wanted to compare more than two groups? Okay, let's say that we have a class of 30 students and we want to compare different teaching methods. And we're going to use this example throughout this presentation. So let's say we have Class A as a traditional lecture method, Class B is video lessons, and Class C is hands-on lesson. Okay. Now to make it simple, I've used these numbers. Obviously, we would not take a class of 30 and divide up and teach them three different ways every day. But for the sake of this lesson, this could be three classes, and we're using these different methods. Okay. We want to see if one or more classes differed significantly on the district-created assessment at the end of the unit. Okay, and I put in parentheses that this is valid and reliable, so we know that this test is a valid test. It measures what it's supposed to measure, and it is reliable. It has been done numerous times, and it's consistent in its reporting. Because we have 3 groups, though, we cannot use our t-test, because that, as we know, was designed for 2 groups. So when we have more than 2 groups, we're going to use what is called our analysis of variance, or ANOVA for short, A-N-O-V-A, ANOVA. And in the ANOVA, this is what our null hypothesis is going to be. Our null hypothesis is that the mean of 1 equals the mean of 2 equals the mean of 3, and so on, until ultimately equals the mean of k. Now, when we say mean of k, we're talking about our kth group. K is the number of groups we have. So if we had 4 groups, it would be the mean of 4. If we had 10 groups, it'd go up to the mean of 10. Okay, but k is our universal number for the number of groups that we have. So keep that in mind. So our null hypothesis for ANOVA is going to be that the mean of each group is equal to the others. Okay? So let's talk about variance for just a minute here, and let's refresh what we've discussed about variance, because obviously in the analysis of variance, this is one of the key things which we are examining. So let's make sure we understand all that we've been discussing about variance up to this point. So as we have discussed numerous times, variance deals with the amount of dispersion among our scores around the mean of our scores. So up until this time, we've been talking about a single group and how much the scores vary within that group. In other words, how spread apart are they from the mean of that group? And what we've learned that is a low variance indicates that the scores are close to the mean, and that a larger variance means that the scores are further apart from the mean. They're spread out relatively. Okay, and so make sure you understand that concept of variance. You know, how close or far apart are our scores from the average score within the group, however we define the group. If we can isolate our means, which we can, and then we can, once we do that, we can determine our variance, which we can also do. Then we can determine the probability of events happening randomly. And the way that we do this is we want to look at the probability that deals with overlap of our groups. And we've looked at visuals. We're going to look at some more visuals on this. But that's what we're looking at, is once we can isolate our means and determine the variance, then we can determine the probability that these events that we're looking for happened at random. Significant differences in our means, meaning that they are not close to each other. And I always say relatively here because it depends on what we're looking at. But just conceptually, if we have significant differences in our means and low variability, meaning that our means are spread apart and our scores with low variability are centered around the means, then there's very little overlap between the 2 groups that we've been looking at. And we're going to see this is similar to ANOVA when we're looking at 3 groups. If that is the case, then it's easier for us to determine with confidence that what we're seeing is significant. Okay? So theoretically, if we have 3 groups, we could use multiple t-tests. So we could compare group Class A to Class B, Class C to Class B, and then finally Class A to Class C. And so theoretically, we could do that and carry out these multiple tests, but feasibly, we wouldn't want to do that if we had more than just the two groups. But we also, it's the simple idea that an independent t-test would indicate that we're using that and that group data in an analysis only once. Okay, and so theoretically, it doesn't fit that we would do multiple t-tests, and so we need to use something different. If we have more than one group, it would be correct to compare all variances and means once, and that can be done through analysis of variance. Okay, so instead of doing those separate independent t-tests, we're going to do everything at once. And theoretically, that would be the best way to go, and so that's what we're looking at. So I want to give you some rationale for why we would use an ANOVA, okay? And this is going to give us some of the background here. So when we look at our total group of students, and this is our big N equals 30, we can come up with a grand mean for the whole group. We can still find normal descriptive statistics for our whole group, such as the standard deviation, the variance, and the sum of squares of the deviation scores. We can find all that for our whole group. When we do it for the group as a whole, all notations dealing with our group are going to have a subscript of a capital T to indicate totals, such as X bar subscript T. Okay, this is the mean of our total group. So that's the first thing that we get here, is that we can look at our total group, all three classes, as one total group. Okay, important to understand that we can treat everything as one large group. And we have a grand mean, and we have all these other grand totals. Number two, when the total group of 30 students is divided into their individual groups, the total variance of each group is also divided. So in the previous slide I said we can have a grand mean, and we can look at all types of things, the grand deviation, the grand variance. But when we divide the groups into their respective areas, so here we have three groups, then what happens is that each group takes its own variance with it out of the total. So some of the total variance goes to Class A, some of it goes to Class B, and some of it goes to Class C. And this we refer to as within group variance. And so what this means is we're looking at the measure of dispersion within the groups around the individual group means. So within group variance, and we're going to use this phrase within a lot. Within group means we're talking about the individual groups. So the individual Class A, the individual Class B. So within group variance for Class A is the variance that goes with the 10 students that are just in Class A. Okay. This is also referred to in statistics as error variance. Now remember, this, when we talk about error, we're not talking about a mistake. We've never been talking about a mistake. We've used the term error quite a bit, but it's never about a mistake. It's just unexplained variance that we have in whatever it is that we're dealing with. Okay. The important thing here is that so from the previous slide, we can look at the groups as a whole, our grand, mean, and so forth. From this slide, when we divide the groups have some of the total variance they take with them, and we call that within group variance. That's the individual variance they have within their individual groups. And so here is an example of what that looks like visually. Okay? So you can see here is our grand mean, our total mean, and our total variance. You can see as we're going from side to side, when we divide up into groups, you can see that each group has its group mean. Here's the mean of A, the mean of B, the mean of C, and you can see that I have drawn the variance for C, indicating that the variance for C is only within C and B, so forth. So this is a visual example of what within group variance looks like. This is what we're talking about. We're not talking about the big variance of the group as a whole. We're talking about within the individual groups themselves. So the other part of that variance then, of the whole group, is the total variance of each individual group around the mean itself. And this is called the between group variance. So visually, this was that first one that we looked at. Okay, so this is the variance around the grand mean. And we should probably take away those bars there in group B. But we're looking at how the individual groups themselves. Now I know I put that there. So this is just showing how the individual scores within the groups relate to the grand total. Okay, and this we call between group variance. So within group, the variance, we're talking about the variance within the individual groups. Between the groups, we're talking about the variance of the groups compared to the grand mean. Okay, and again, we'll come back and we'll talk about those terms and we'll use them quite a bit. And finally, the last rationale then is eventually the variance between the groups will be compared to the variance within the groups to gauge if there is a significant difference that exists. And we're always working with probabilities, and so we're wanting to know what the probability of the difference that exists happened randomly or not. So let's take a look at our hypothetical data from our classes. So here is our class score, and let's look and see what all we have here. Class A, this is their scores. We have 10 students in each. These are the scores for A, the scores for B, the scores for C on our test. We have a sum. We want to sum our scores. We always want to get sums. We have the average. That bar should be going across there, but it's not, but that's fine. You can see the average of A is 77.4. The average of B is 85.3, and the average of C is 74.5. We have an N of 30. Now, the sum of x and the sum of x squared, we need to go to the next slide to look at this. So what we did here simply is we take our x, our score for A, and square it. Okay? We do the same for B, and we do this every score, and we get a total here for the sum of all our A scores, 60,000, all our B scores, 73,000, and all our C scores, 55,000. And we square those, or we add them up to get a sum of x squared, which is 188,808. And the sum of our scores, of our individual scores, we would add all three grades together, and we get 2,372. So we have talked about in the past the sum of squares being the deviation from the mean, but we're going to use a slightly different definition here when we're talking about sum of squares. So you can see that I've already indicated to you that we're going to take our individual scores and we're going to square them. That's an error right there, obviously, but we're going to square them, and then we're going to add them up for each group, and then we're going to add all the group sums together to get a sum of squares here. So on the next slide here, you can see that we have our basic formula here, our sum of squares, and we've used this in the past, but in the past we've been referring to again, the deviation of the individual scores from the mean. So here it's a slightly different take on that. Here we're looking at those scores squared and actually summing the squares of our scores. Okay? So our formula is straightforward. The sum of x squared minus the quantity x squared, the sum of x over squared over n, our n. And we can input the data then that we find from our table, that we can get from our table, and we're going to call this the sum of squares total. So let's go back to our table real fast. So here's our sum of squares, or the sum of our scores, 2,372, and that's simply adding every score in all groups. And the sum of our squares was 188,808, and our n is 30. So now let's go look at that formula, and when we input these numbers, we come out with 1,261.87. This is the total variance for our whole group, all group. This is our sum of squares total. So when we're talking sum of squares, we're talking about variance. And our total variance now is 1,261.87. Now we want to see how this is made up by looking at those variants that we talked about in the rationale when we said we had group, within group, and between group variances. So how do those two things add up to get our total variance of 1,261.87? So let's take a look at these two things and determine how we can figure these scores. We're going to use this same formula, the sum of squares. We're just going to change it based on whether we're looking within a group or we're looking between groups. Okay, so in order to understand the variance, the two groups that make up the total, the within group and the between group, we're going to figure those separately. And if you have the PowerPoint, this is a hyperlink that will go back and explain the within group variance again. And remember, this is the variance within the individual groups. So you can click on that and it goes here. And then when you're done, if you click on the end of the sentence here, it'll take you back. But you can see here, this is the variance within the individual group. So we need to figure that total variance. And we do that by simply taking our formula that we just used and applying scores from the individual classes. And that was all in our chart. So the sum of squares for A, the variance is 184.4. For B, when we put it in, it's 252.1. And for C, it comes out to 200.5. And so when we add these three together, 184, 252, and 200, we come out with a total variance of 637. So this is our sum of squares within. So this is the variance that we can account for within the individual groups, 637. Okay? Now the next thing then would be looking at the variance of the groups around the grand mean. So this is between. And again, we can go back here and we're looking, here's the grand mean, and then this is the variance within the groups compared to the mean itself, not within the groups themselves. But we're looking at the mean of the whole group. And there's your little dot to go back. And so here, to examine this, now this won't happen in reality, but for the sake of understanding how this works, I want to show you what we're going to do. To examine this, we're going to get rid of all the variance within the groups themselves. And what we're going to do is simply replace all the scores with the mean. By doing this, there will be no variance within the groups. The variance will be 0. So if we look at our next slide, you can see that's exactly what I did. Okay? So we said that the class mean of A was 77.4. So we made all the scores 77.4. And the same for B and the same for C. And by doing this, we have absolutely no variance within the groups. And that should make sense to you, because if the scores are all the same, then there's nothing that's going to be different. Okay? And so when we go to our next slide, it's going to change slightly our sum of x squared. So we follow the same procedure. We take our score and we square it, and this time you can see it's actually all the same. And we sum it up, so this is the sum of all of our A scores squared, all of our B scores, and all of our C scores. So our sum of squares has changed slightly because of the way that we did this, but this is again just to illustrate what we're doing. And so now when we apply our formula to get our sum of squares between, this is the variance between the groups and the grand mean, we get this. Okay, there's the sum of our x squared. There's the sum of our x's, and when we square it and divide it by our n of 30, we get 624.8667. Now look at the next slide. Our sum of squares total is equal to 1,261.8667. We did this earlier to get that total. What we've done in the meantime is we figured out that our sum of squares within was 637 and our sum of squares between was 624. When we add those two together, that comes up to our total. Okay? So what we've done for the last 30 minutes or so is just walk you through the basic process of how the sum of squares works. So now, what are we actually examining? What happens in an analysis of variance is that we're looking at the two aspects of variance here. We're looking at the between group and the within group. And these are displayed on the next slides. Our goal is to measure if the between group variability is larger than the within group variability. If this is the case, we can make a determination there's a distinct difference. So we want to see if our between group, comparing the groups around the mean, is larger than the variability that's within the individual groups themselves. And if that's the case, we can make a distinction that there's something significant happening. So this is similar to a t-test when we said the greater the distance between the means and the smaller variability of the two groups, the easier it is to find the distinct difference. Here we're saying that the larger group variations, the larger between group variations, and the smaller within group variations, the easier to see the difference than if the opposite were true. So here's the first slide, and again, it's just, I'm a visual person. So if we have that larger between group, and you can see our variability between the groups is large here, and so we've spread them out. And the smaller within group, what happens theoretically is we have smaller areas of overlap. Okay? Now let's compare that to what happens if the opposite is true. If our between group variability is low and our within group is high, then it pushes them together and you can see the overlap is greater. When this happens, it's harder for us to make that distinction and say that something is significant. And we would most likely, or we would be more likely to fail to reject our null hypothesis in these cases. So that's really what we're doing, is we're looking to compare the between group to the within group and see if the between group is large enough that we can, when comparing it to the within, that we can make a distinction. So one can see from these two slides that we are looking at variance. ANOVA compares the between group to the within group variance. How do we do this? Well, we've already seen when we talked about variance with independent t-tests, we needed to see if the variances were the same for the independent t-test. And so we created, we found our f value, and then we compared that to our critical f. Well, that's the same method that we're actually going to use here in ANOVA. We're going to look at those two variances. If we find the between group variance is significantly larger, then what will happen is we will reject our null hypothesis and conclude that there is some difference in the means. So there are two things that we must consider when conducting an ANOVA, and we've been talking about these up to this point. Both the between groups and within group variances need to be computed, as we've done. And in the context of ANOVA, variance is going to be referred to as mean squares, or MS. And so we've also discussed degrees of freedom. So degrees of freedom, we've used it almost since the beginning of our class. Degrees of freedom are pretty straightforward in our one-way ANOVA. The sum of squares of deviations, we divided the sum of squares by degrees of freedom. We also used degrees of freedom in examining t-tests and so on. Degrees of freedom are also used within ANOVA, and here's the basic way it's done. It's very easy. The degrees of freedom total, designated as with the subscript t, is n minus 1, where n is our total subject, so that makes sense. Degrees of freedom between is k minus 1, where k is the number of groups. And the degrees of freedom within is n minus k, where n and k are defined as above. N is the total number of subjects, and k is the total number of groups. So we can plug in our numbers that we have for our class of 30 here. Our degrees of freedom total is 29. We had 30, so we 30 minus 1. Our degrees of freedom between is 2. We have 3 groups. 3 minus 1 is 2. And our degrees of freedom within is n minus k. So 30 minus 3, 30 subjects minus 3 groups is 27 degrees of freedom within. And so on this next slide, what we start to see is the beginning of what we call the ANOVA summary table. And so you can see here from this table our sources of variance, our degrees of freedom, and our sum of squares. So these are the things that we have determined up to this point. We looked at our total variance, then we broke it down and found our between group and within group. What's missing here is our mean squares and our f value. So let's quickly figure these last two columns. These are fairly fast because we've done these already. So earlier we stated that variance in ANOVA is referred to as mean squares. To compute the mean squares, one simply divides the sum of squares by the degree of freedom for the between group and then for the within group. So there will be 2 mean squares. And this is what our formula looks like. The sum of squares divided by the degrees of freedom. So we do it for each group, the between and the within. And so if we plug our numbers into this formula, here is what we get. Our mean squares between is the 624.87 divided by 2. And our mean squares within is 637 divided by 27. And so there are our mean squares between and mean squares within. Now let's look at our chart once more with our mean of squares added. And so now we see that our between group mean of squares is 312.44, and our within group mean squares is 23.59. So how do we determine our F value? Remember, this is variance. We learned in the last chapter we divide the larger variance by the smaller, and we do the same here. And so dividing 312.44 by 23.59, we get an F value of 13.24. So we can add that in and we can complete our ANOVA summary table. Okay? So you already know what the next step is. If we have an F value, we have to look and determine what our critical value of F is using our charts. So we find our F critical value the same way we did when we examined variance to determine if the variances were equal or not. We use the F distribution and look at the top using the our numerator degrees of freedom, and then go down the side using our denominator degrees of freedom. So this is real simple. Our degrees of freedom are 2 and 27. When we do this, we find our critical value of F is 3.35. So our F value is 13.24. Our critical value is 3.35. This means that our F value has exceeded the critical value. So therefore, we reject the null hypothesis that we started with that said the means of each were equal. The mean of A was equal to the mean of B, which is equal to the mean of C. So there is some significant difference here, but where does that difference lie? Is it between A and B? Is it between A and C? Is it between B and C? We don't know where that significance is. So unfortunately, we're not quite done yet. Okay, so this is not the end. So the end is very close, though. I promise you it's very close. So we have determined that the means of the three groups are significantly different. P is less than 0.05 at the 0.05 level. We learned this from the grand mean. We used the grand mean in looking at this. But what we did not do is we did not look at the individual group means. And it is not obvious how the groups compare to each other. So we learned there's the difference, but we're not sure where that difference is. So to find this actual difference, what we're going to do now is compare individual groups and see if we can locate where this difference lies. And it may be in one spot only, it may be in multiple spots. So up until this point, you've heard me refer to we're doing a one-way ANOVA. There are multiple forms of ANOVA methods out there. Another one is a two-way ANOVA. We're looking at one-way ANOVA. The one-way means that we only have one independent variable with two levels. In our example, the independent variable was the instructional delivery, and we had two levels of treatment. We had a video and we had a hands-on, and then of course we had a control group. Okay, so our independent variable is our delivery. Our dependent variable was our test scores. Our test scores were dependent on our delivery. In a two-way ANOVA, you have two independent variables with multiple levels. And to just give you an idea of what this means, you could be studying a diet in different age groups by looking at exercise and meditation. Okay, exercise could have no exercise up to 3 times a week and more than 3 times a week. So you can have 3 levels of exercise that you're comparing here. Meditation can be simply a binary yes or no with 2 levels. So this would require us to do a two-way ANOVA, and there is a little bit of more computations in there, looking at error within the independent variables, the variance and the variance that we can't account for, and so forth. But this is out of the scope of our class. So know that you're going to hear one way and you're going to hear two-way ANOVAs. And what you're learning here is a one-way ANOVA. So what we do now that our ANOVA has told us there's a difference is we conduct what we call a posteriori or post hoc test. And once we determine there's a significance, we need to determine where that significance lies within the groups. There are a number of post hoc tests that do these pairwise analyses, and we're comparing each pair to the others. We're only going to look at one group or one post hoc test, and that is called the Sheffa test. And you can see at the chart below that we're going to compare A to B, A to C, and B to C. Those are the only comparisons we need. And this is the formula that we use for Sheffa's procedures. And we're going to create or find an F value by comparing our two individual data points from either A or B, or A and C, or B and C. And we're going to come out, you see, we'll use the mean squares within, we'll use the number of groups we have. We're not going to go through and do all of these data. We know all of our numbers from these data. We can look at our summary table and get them. And so we can look at, you can do this. We do have an F critical already. We use the same for our ANOVA, 3.35. And so you would just plug those data into that formula and then use your F critical from your ANOVA and see what they are. If any comparison of the groups exceeds the critical value of 3.35, then we fail to accept our null hypothesis and we say there's a distinct difference between those groups. Otherwise, we accept our null hypothesis and say there is no difference, that group X is the same as group Y. Note one thing here. This test, the Sheffa's test and the numerous other tests, are not as powerful as the ANOVA itself. And so there might be a chance that you could run a post hoc test and not show any significant differences among the groups. If that were the case, then what you would do is simply say the difference exists between the two groups that have the largest separation of means. Okay. So let's complete our chart. Notice we only have 3 comparisons to make. So when we do the Sheffa process, we fill our numbers in here, and you can see that the difference in Class A and Class B was 6.61, and I put an asterisk out there to show that it was significant. Class A and Class C was 0.89, not significant, and Class B and Class C was 12.36. So our results showed that there was no difference between A and C, but that there was a difference between B and A and B and C. So we would conclude, after our ANOVA, that Class B, using the videos, yielded significantly higher scores than either Class A or Class C. And if you wanted to put it into Excel, you can use Excel and use the data information, and it looks like this. Okay. Notice I highlighted that our ANOVA single factor is what we use. It's not called one way, it's called single factor in Excel. And there's our F critical and our F value that was calculated. So let's look at our goals real quick for our course. We've covered a lot of material. So our goals were Compare and contrast the purpose of analysis of variance. Discuss the rationale for the analysis of variance. Compute the necessary values to complete an analysis of variance summary table. Determine when an a posteriori test is appropriately applied. Interpret the statistical significance F value from an analysis of variance. Use the F table to determine the critical value, and describe the two components of variability in the analysis of variance, the within and between. So we've covered a lot of material. Like I said, this is a very important this is a very important test, like I stated, and so we're going to spend some time reviewing the exercises that go along with this module.